Hi, so this video is going over how to find an inverse of functions algebraically. We're only going to do a couple basic examples and we'll do some more complicated examples in class together. So in order to find the inverse of a function algebraically, if it starts with f of x, you're first going to replace f of x with y. Very simple step because these are the same thing. Now remember what we learned. We said yesterday that the domain of the original function becomes the range of the inverse function. So therefore, all of your x's become your y's, all of your y's become your x's. We said if a point AB lies on the graph of f, then the point BA lies on its inverse graph. So therefore, we're interchanging x's and y's in our equation, and then you're solving for your new y value. And then finally, you're going to replace it with f inverse of x, and then you can always check it by doing the composition both ways. That part is optional, but obviously that's a great way to double check your final answer. So if we want to find the inverse here, again, first step is to replace f of x with y. You don't have to do that unless you want to, because now we're just flipping our x's and our y's. So wherever I see a y, I put an x, and wherever I see an x, I put a y. Now our goal is to get this y value by itself by undoing the equation. So our first step here, we want to get rid of the fraction. So since we're dividing by 2, we're going to multiply both sides of our equation by 2. And by doing that, our 2's will cancel. So now I'm left with 2x equals 5 minus 3y. From here, again, we're getting y by itself. So the next thing to move is the 5 to the other side by subtracting 5. So now I am left with 2x minus 5 equals negative 3y. And lastly, to get this y by itself, we need to get rid of the negative 3. So we're going to divide both sides by negative 3. So now we get y is equal to the quantity 2x minus 5 divided by negative 3. Now we have isolated our new y value. So our final step is that we're replacing y with f inverse of x. So my final answer is f inverse of x is equal to 2x minus 5 divided by negative 3. And we can just leave it like that. We're going to do one more example, and then I have a couple for you to do on your own. So number 2, we have f of x is equal to 5x minus 7, and we want to find the inverse. So again, we can replace f of x with our y value. You don't have to do that as long as you know f of x is equal to y. But now we're going to flip our x's and our y's. So now we have x equals 5y minus 7. So again, you interchange where x and y are. Nothing else has changed. Now we're going to solve for our new y value here. So the first thing that needs to happen is to get the 7 to the other side. So we're going to add 7 to both sides. And we are left with x plus 7 equals 5y. And now to get this y by itself, we need to get rid of the 5 by dividing by 5. So we get y is equal to the quantity x plus 7 over 5. And then finally, we do f inverse of x is equal to x plus 7 over 5. So these are just the basic problems. We are going to do something a little more complicated on Thursday. But I also want to take a look at number 4. We can do that one. We'll jump back to number 3 together. So number 4 says we want to find the inverse of the square root of 2x minus 3 algebraically, and then we're going to sketch both those graphs. So again, first we have y is equal to the square root of 2x minus 3. And now we're substituting our x in for y and our y in for x. So I have x equals the square root of 2y minus 3. Again, nothing else has changed. Now I can get the y by itself. So the first thing to get rid of is the square root. In order to get rid of the square root, we need to square both sides so that they will cancel. And now I'm left with x squared is equal to 2y minus 3. I now move the negative 3 to the other side by adding it. So I get x squared plus 3 is equal to 2y. And then lastly, I am dividing by 2 here. So I have y is equal to x squared plus 3 over 2. And we just want to write that in function notation. F inverse of x is equal to x squared plus 3 over 2. Now I want to show you what is unique about this. And today you should have just learned about this algebraic inverse, solving that. But this is a unique problem because we want to sketch these. So let's see what happens when we sketch this graph that we were given, the square root of 2x minus 3. A couple things that we can note is that if we found the domain of this, we would have that it is all numbers greater than or equal to 3/2. So if I have 3/2 and plug that in, I get 0. A couple other points, if you plug 2 in, 2 times 2 is 4, 4 minus 3 is 1, and the square root of 1 is 1. And then if we plug 3 in, 3 times 2 is 6, 6 minus 3 is 3, so this is the square root of 3, which is about 1.7. You could plug more in, but if I plug 4 in, 4 times 2 is 8, 8 minus 3 is 5, so we're looking at the square root of 5, which is about 2.2. So if I plot these points, so 1.50, 2, 1, 3, 1.7-ish, 4, 2.2-ish, we're looking like that. Now remember, again, our x's become our y's and our y's become our x's. So our inverse is going to change our values. Now we're going to have 0, 3/2 as a point, 1, 2 as a point, about 1.73, and then about 2.24. So it would look like that. And then you can see it is reflected over this imaginary line of y equals x. So the way to get that, the reason this is the case is the domain of my original, this is my domain here, becomes the range of my inverse. So my domain is x is greater than or equal to 3/2. You can see that the range of the inverse is now y is greater than or equal to 3/2. Whereas the range of my inverse, we can see it's all numbers greater than or equal to 0. That becomes the domain of my inverse. So all numbers greater than or equal to 0. So here, our inverse, keep it in blue, has a domain from 3/2, from 0 to infinity, and a range from 3/2 to infinity. Whereas our original function here had a domain of 3/2 to infinity and a range of 0 to infinity. So that was just a little extension. Again, you should know how to solve them algebraically, and you'll have a couple problems to complete.